Before we get into the heart of the material in this section, I just want to remind you of the importance of your algebra skills. I could go on and on about this, but there are three things I'm going to mention in particular and things that you need to work on if you think you have deficiencies. First thing I'm going to mention is changing radicals into fractional exponents. The general power rule for integration, in which we'll be using, deals with things raised to powers, not radicals. So we have to make that change in order to apply the general power rule for integration. For example, if you had this integral where the integrand is the cube root of the quantity 2x plus 1 squared, then you've got to convert that to a fractional exponent before you can do anything with it calculus-wise. You have to know the property that applies that says the nth root of a to the m is a to the mn. The root becomes the denominator of the fraction that represents the exponent. The power is the numerator of that same fraction. So here, for instance, I would change that cube root of something squared to that thing to the 2/3 power. Notice that the 3 goes into the denominator and the 2 goes into the numerator. If any of that looks like something you're not comfortable with, before you dive into this section material, go back and practice that and make sure that skill is up to par. Second thing I want to mention is the ability to rewrite certain rational expressions using negative exponents. For example, if you had a fractional integrand like this, that quantity x to the 5th plus 1 raised to the 3rd power in the denominator needs to be rewritten at some point before you can deal with it using our integration formula. Namely, you need to change that power of 3 in the denominator to a negative exponent using the property that 1 over a to the n power is a to the minus n. So that quantity x to the 5th plus 1 to the 3rd power in the denominator, if you push it up, it becomes a minus 3. And now the fraction is gone, and you've got an expression with a base raised to a negative exponent. Again, a second skill that you need to be able to apply easily, and if you think you need practice on that, it's worth the effort to go back and review that skill. The last thing I'm going to mention, and there are many others I could, but the last thing I'm going to mention here in terms of preliminary algebra skills that you need is knowing how to deal with a constant factor inside of an integrand. As an example, what if I had 4 times the quantity 2x minus 3 cubed as the integrand? There are various things I can do with that 4, which is a numerical factor. It's a number, and it's multiplied by the expression of the power. I need to know that I can either factor it completely outside of the integral sign, which is probably in reality what I'm going to do most of the time, but I can even move it around within the integral if I want to. So one thing I could do with that 4, and what I will be doing most of the time, is factoring it outside of the integral sign. You need to know that that's okay. You could actually move it around within the integral sign, and sometimes that's useful, and not just for a constant. As long as you don't pull it out of the integral sign, you can move any factor around inside the integrand. So you need to be comfortable with dealing with numeric factors within an integrand. Now, like I said, I could mention lots more things. Your algebra skills, I'll just say the better you are with your algebra, the easier time you're going to have with the calculus. But these in particular are things that come to mind as things that cause students sometimes more trouble than the calculus itself. I want to go back to this word factor before I close out on this. Factor implies multiplication. So when I say that you have a numeric or a constant factor, what I mean is being multiplied by something. So for example, if you have the expression 4x, 4 is a factor of 4x because it's multiplied by x. But if I have the expression x plus 4, 4 is not a factor, that's a term. It's not a factor. So what I say about factors being factored out of an interval only applies when the number is multiplied, not when it's just plus something, minus something. It's got to be a factor. So for instance, if I wanted to express the interval with an integrand of 4x in another form, I could pull the 4 outside of the interval sign. Perfectly okay. In fact, I'm going to be doing that a lot in this section. What you're not allowed to do is do the same thing with a term. That 4 in the x plus 4, you cannot simply push it outside of the interval sign. Factors, yes, numeric factors can be pushed outside the interval sign. Terms, no. Factor implies multiplication. I really encourage you that if you need to review or practice or come for help on any of these algebra skills, do it now. Don't wait till these difficulties have caused you to build up a series of poor scores. Get the help now while there's still time to use those skills to improve your grade and to make your life easier when you're doing the problems in this section. So take that seriously and review, practice, get help as needed before it's too late and causing you problems. Now it's time to tackle some more challenging intervals. What I'm going to do now, I will label integration method 1 and refer to as guess and check, and it's based on the logic of what we were doing when we were working with antiderivatives and thinking of an antiderivative as being found by reversing the process of taking a derivative. And if you feel comfortable with that, you're going to feel more comfortable with what I'm calling here guess and check, and it'll provide a much easier transition to some of the later methods that we'll use to handle intervals that are a little more complicated than even what we're dealing with right now. And the best way to handle this, I think, is just start off with an example. Suppose I want to evaluate this integral, whose integrand is 8x times the quantity x squared plus 1 to the third power. I want to think about the thought process that someone would go through that might be using this method. First of all, I would say, look, I see something raised to the third power in that integrand, and I realize from past experience with antiderivatives that when I'm taking something to a power, if the derivative lowers the power by 1, an antiderivative or an integral will increase the power by 1. So I'm going to take this educated guess that the integral here will have the expression x squared plus 1 raised to the fourth power instead of the third power because it goes up by 1. Now you can't stop there. This is just an educated guess. I have to check it and see if I'm right or wrong. How do I check it? I check it by taking the derivative of my guess. The derivative of the expression x squared plus 1 raised to the fourth power. By the power rule for differentiation, the 4 comes down, the base is written down, the 4 drops to a 3, and you come back and take the derivative of the base. The base is x squared plus 1, whose derivative is 2x. And then, of course, the 4 times the 2x becomes 8x. So I'm trying to check to see if my guess is right. Well, what do I mean that guess is right? That means it matches the original integrand. And if you look back to the original integrand, does it match exactly? Yes. So my intuition or my educated guess was exactly right. That means the correct answer is what I guessed, which is the quantity x squared plus 1 raised to the fourth power. You always have to put a plus c because, again, thinking of this as reversing the differentiation process, there could have been any number added to this quantity x squared plus 1 to the fourth, whose derivative would make that constant vanish, so we'll always have to add a plus c. It's possible, though, that this guess and check method will work even when my educated guess is not exactly right. So I want to take an example of that, and the easiest thing to do might be to take the example we just worked, except knock out the 8 and change it to something else. What if I make it a 4? So this example is almost exactly like the one before. So the process is the same. I go through there and I make a guess, an educated guess, by realizing that the power of 3 will probably go up to 4. So my guess, just as before, is the quantity x squared plus 1 to the 4th power. What do? I have to check and see if my guess was right, and I do that by taking the derivative of my guess. Well, that's exactly the same thing I did before, so I'm not going to make a big deal out of it. The derivative would be 4 times the base raised to the 3rd power multiplied by the derivative of the base, which is 2x, and that's exactly the same calculation I just went through, and I get 8x times the quantity x squared plus 1 cubed. But this time, when I look back to see if it is an exact match, I see that it's not. I have an 8 in my derivative of my educated guess, but I only wanted a 4. Is all hope lost? Well, the answer is no. If you're only off by a numerical factor, just a number factor, and here I am, I wanted a 4, but I got an 8. I'm only off by a numerical value. Then there's hope to make an adjustment to my guess and still get it right. So if I had an 8 and I wanted a 4, maybe if I put a 1/2 in front of my original guess, that would reduce the 8 to a 4 when I do my check. Well, let's see, does it? I have to check it out by taking the derivative of that guess, in this case my adjusted guess. So now I'm taking the derivative of the expression 1/2 times the quantity x squared plus 1 to the 4th. Still, I'm using the power rule for derivatives. 4 times 1/2 is 2. Write the base down, the x squared plus 1. Drop the 4 down to a 3, and then multiply by the derivative of the base, which would be 2x. Now, simplifying, 2 times 2x is 4x, and now when you compare, you get exactly the same as you started out with in the integram. So my adjusted guess was correct. My original guess was off by a constant, but my adjusted guess is spot on. It's exactly right. That means my adjusted guess is the answer. My original guess was off by a factor, but my adjusted guess is exactly right. And if it's exactly right, then that is the answer. So you can see this guess and check method is powerful, but it's also just a logical extension of what we did with antiderivatives. So for the simpler problems, this guess and check method is a perfectly reasonable way to do the problems, and you can take it as far as you want. Later we'll learn some more formal procedures that can replace the guess and check, but you're free to use this guess and check as far as you're willing to take it. Now I do want to show you an example where the guess and check method fails you, because you can only be off by a constant. So let's look at an example where guess and check is not going to get you there. So suppose I have this interval. I want the integram this time to be 3x times the quantity x plus 1 squared. I start off exactly the same, try my guess and check. Nothing different about the process at all. I see that expression with a power of 2, so I'm going to guess that the power goes up to 3. So my guess will be the quantity x plus 1 to the 3rd power. What do I do next? I check to find out if my guess worked. I do that by taking the derivative of my guess. The derivative of the quantity x plus 1 to the 3rd is 3 times the base to the 2nd, and then you multiply by the derivative of the base, which happens just to be 1 here. So you end up with 3 times the quantity x plus 1 squared. Am I right? If you look back up there, no, I'm not right. And in fact, I have a real problem because I'm off by a factor of x. Now, as I said earlier, you can adjust this and fix it if you're only off by a numerical factor, a number. X is a variable, and if you're off by more than a number, if you're off by something that involves the variable, then guess and check fails. And if guess and check fails, you have to either try some other method or just admit that you don't know how to get the answer. I just wanted to show you that guess and check doesn't always work. There are cases where the method doesn't work, but it's easy to see where the failure happens. It happens when you're off by more than just a number. Suppose I want to evaluate this integral, x minus 6 quantity to the 3/2 power. And suppose I want to do it by the guess and check method. What you have to remember is guess and check involves guessing the antiderivative, the integral, then checking your guess. If it matches exactly, then your guess is the answer. If it's off by a constant factor, just a numerical value, you can adjust that in your guess, we'll call that the adjusted guess, by using the reciprocal of what you're off by. Then check that solution by taking its derivative, making sure it matches the original integrand. If it does, then that's the answer. If you cannot get a match within a constant, just a numerical value, then guess and check doesn't work. In general, we're going to be using guess and check on the easier of these problems in any case. So you always have other choices. We're going to be, generally speaking here, using the general power rule for integration as our model for our guess. And the reason is, when you have an integrand raised to a power, the general power rule for integration tells you that the solution will have a power 1 higher than the power in the integrand. So when I'm doing this problem, I'm going to guess, let me just copy it back down here for easier viewing. I'm going to guess that this solution will look like x minus 6 to the 1 higher power than 3/2. Now, I hope you don't have to think too much about this. Remember, when you're adding 1 to a fraction, in this case 3/2, 1 is like 2/2, so you end up with an exponent of 5/2. So my guess will be 1 higher exponent than the original. 3/2 plus 1 is 5/2. Now I have to check that guess. How do I do that? I take the derivative of the guess. You should be good at derivatives by now. That would be 5/2 times the base to the 1 less power, just working backwards from the calculation we did a minute ago. 1 less than 5/2 is 3/2, and then the derivative of the inside is 1. So you end up with 5/2 times the quantity x minus 6 to the 3/2 as my check. So does it match exactly? And the answer is not quite. You have the x minus 6 quantity to 3/2, but you don't have a 5/2 in the integrand. There is no 5/2 there. So you didn't get an exact match. What do you do when you don't get an exact match? Well, you make an adjusted guess. Your adjusted guess will take into consideration what you are off by. You are off by a factor of 5/2. Generally speaking, you will adjust by the reciprocal of what you are off by, factor-wise. The reciprocal of 5/2 is 2/5. So my adjusted guess is going to be 2/5 of what I originally guessed, which was the quantity x minus 6 to the 5/2. And then I have to check that guess. Checking the adjusted guess, I again take the derivative of the adjusted guess. By the power rule, you take the exponent times the coefficient. That's 5/2 times 2/5. Write the base down, x minus 6, and reduce the power by 1. As we've discussed, 5/2 minus 1 is 3/2, and then the derivative of the inside is just 1. Notice that 5/2 times 2/5, in other words, a number times its reciprocal is always 1. So you end up with just the quantity x minus 6 raised to the 3/2 power. So that's your adjusted guess. Does it match the original problem? Well, look. The original integrand and our adjusted guess's derivative are, in fact, an exact match. Exactly. That means my adjusted guess was right. What was my adjusted guess? My adjusted guess was this 2/5 quantity x minus 6 raised to the 5/2. If it's exactly right, then that is the answer. So the answer is the quantity x minus 6 raised to the 5/2 power. And don't forget, as always, you still have to put a plus c, because thinking backwards, the derivative of any number is 0, so there could be any constant added onto the end. And there is the answer by guess and check. Suppose I want to evaluate this integral, the integral of 2 times the quantity x minus 6 to the 3/2 power. And suppose I want to do it by the guess and check method. What you have to remember is guess and check involves guessing the antiderivative, the integral, then checking your guess. If it matches exactly, then your guess is the answer. If it's off by a constant factor, just a numerical value, you can adjust that in your guess. We'll call that the adjusted guess, by using the reciprocal of what you're off by. Then check that solution by taking its derivative, making sure it matches the original integrand. If it does, then that's the answer. If you cannot get a match within a constant, just a numerical value, then guess and check doesn't work. In general, we're going to be using guess and check on the easier of these problems in any case. So you always have other choices. We're going to be, generally speaking here, using the general power rule for integration as our model for our guess. And the reason is, when you have an integrand raised to a power, the general power rule for integration tells you that the solution will have a power 1 higher than the power in the integrand. So when I'm doing this problem, I'm going to guess that the integral will have a solution with a power 1 higher than 3/2. And of course, 3/2 plus 1 is 3/2 plus 2/2, which is 5/2. My guess will use that as the exponent. And before I actually get started on this, let's copy it down here. So as I said, my guess for this integral solution is going to be the base raised to the 1 higher power. Notice there's a 2 there. I'm going to carry it with me for now, but just follow along with me. My guess has to be checked. How do I check the guess? By taking the derivative of it. Okay, by the power rule, you multiply the exponent times the coefficient. So you get 5/2 times 2. Write the base down. Reduce the power by 1. 5/2 minus 1, which is 2/2, would be 3/2. And then multiply by the derivative of the base, which in this case is 1. If you simplify that a bit, the 2's divide out here, and you get 5 times 1. You get 5 times the quantity x minus 6 raised to the 3/2 power. Does it match the original integrand? And if you look back, it doesn't. Part of it does. The part that has a variable in it does. Notice you get all of that. But the constant is not right. This has a 5. This has a 2. So it did not match exactly. That doesn't necessarily mean that guess and check failed because we only differ by a constant. If you differ by a constant factor, you can adjust. Now, we'll suggest this. If you have a constant in the original problem, like this 2, and it doesn't work out exactly, we got a 5, we needed a 2. If it doesn't work out exactly, I would suggest going back to the general power rule formulation. This a in the formula is like the 2, and I would suggest taking that a and moving it outside the integral sign. We're allowed to do that. We can move a constant factor outside the integral sign. So whenever the initial guess doesn't check exactly, but it's only off by a constant, my suggestion is to rewrite that integral with the constant outside of the integral sign before you continue. So what's going to happen is we're just going to leave the 2 and ignore it until the very end. We're going to work the problem without the 2 in there and then multiply our final solution by 2. So now we're going to make our adjusted guess by ignoring the 2 outside for the time being and just looking at the integral I have boxed in up top there. So I want to guess this time that I'm going to have the x minus 6 to the 5 halves, which is what the general power rule for integration tells me. But because I don't want the 5 halves to show up in the answer, I want to multiply by the reciprocal of that, which is 2/5. So my adjusted guess for the integral in this box up here is going to be 2/5 times the quantity x minus 6 raised to the 5 halves power. As long as I move the 2 out and don't worry about it now, my adjusted guess is always going to be the reciprocal of the power. So if I have 5 halves, it'll be 2/5. If I have 9/5, it'll be 5/9. If it's 5, it'll be 1/5. You're always going to make your adjustment as the reciprocal of the power you're guessing. And now we'll check it. Let's see if that's right. In order to check it, we take the derivative. The derivative is the power times the coefficient. That's 5 halves times 2/5. Write the base down, x minus 6. Reduce the power by 1. The 5 halves minus 1, which is 2 halves, becomes 3 halves. And then you take the derivative inside, which is 1. Notice that 5 halves times 2/5 is always going to be 1 because you're multiplying by the reciprocal. And that's the whole reasoning behind what our guess is for the adjustment factor. And you end up with the quantity x minus 6 to the 3 halves as your adjusted guess check. Now the question is, does it exactly match the integrand? Remember, we're looking at the integrand in this rectangle up here. We're just ignoring the 2 for now. And if you notice, it does match exactly. Look, this and the integrand exactly match. That's an exact match. If you get an exact match, then your adjusted guess is the answer. So that means when all is said and done, remember the 2 is just sitting there. So I want to keep it there. It's 2 times, this 2 is just sitting there, so I have to include it here. 2 times my adjusted guess. Well, what was my adjusted guess? My adjusted guess was 2/5 times the quantity x minus 6 to the 5 halves. Now you always have to put a plus c on the end of any of these indefinite integrals, because if you think backwards, the derivative of any constant is 0, so there could be any constant term added on. You don't know whether it is or isn't, so you put a plus c. And simplifying it one more time, if you multiply 2 times 2/5, you get 4/5. And I'll put the final answer up top here. So you end up with 4/5 times the quantity x minus 6 raised to the 5 halves power plus the constant of integration. And you solve this problem by guess and check. You can solve it by one of the other methods, but for the simpler ones, you might consider this guess and check. If you don't like it, you don't have to do it this way, but at least you want to look at it and consider doing it this way, at least for the simpler problems. Suppose I want to evaluate this integral, and suppose I want to do it by the guess and check method. What you have to remember is guess and check involves guessing the antiderivative, the integral, then checking your guess. If it matches exactly, then your guess is the answer. If it's off by a constant factor, just a numerical value, you can adjust that in your guess, we'll call that the adjusted guess, by using the reciprocal of what you're off by. Then check that solution by taking its derivative, making sure it matches the original integrand. If it does, then that's the answer. If you cannot get a match within a constant, just a numerical value, then guess and check doesn't work. In general, we're going to be using guess and check on the easier of these problems in any case. So you always have other choices. We're going to be, generally speaking here, using the general power rule for integration as our model for our guess. And the reason is, when you have an integrand raised to a power, the general power rule for integration tells you that the solution will have a power 1 higher than the power in the integrand. Before beginning the solution, let's bring down the integral to where we'll be doing the work. The first thing I want to do, if I'm going to in fact use the general power rule for integration and make a guess, is choose my guess to be the base raised to the 1 higher power, because the power rule tells us that if it does apply, the result will end up being of 1 higher power than the original problem. So that'll be my guess. So what do we do next? Of course, we check our guess. How do we check our guess? We take the derivative of it and see if it matches the integrand that we started with. So the derivative of the quantity x squared plus 3 raised to the 4th power would be 4 times the base raised to the 3rd power, and then take the derivative of the inside and you get 2x. Simplifying gives us 8x times the base, which is x squared plus 3, raised to the 3rd power. Now we look to see if it matches exactly. So we take the derivative of our guess and compare it to the original integrand. And if you look at those two things, you can see that they are, in fact, an exact match. So in this case, we don't have to go for an adjusted guess because there was an exact match. When there's an exact match, that tells us immediately that the integral that we guessed is, in fact, the correct answer. So when the first guess actually works, the answer is the guess, which in this case was the base x squared plus 3 all raised to the 4th power. And of course, you always have to put the constant of integration plus c on the end to allow for the fact that the derivative of any constant is 0, so there could have been another number added on. We have to allow for that possibility. So the general solution is the quantity x squared plus 3 raised to the 4th power plus c.